Hi, welcome back to Book Club. We're in, pick your favorite applied numerical methods book. This happens to be a good one with Python. Like I said, on this book club, I'm going to do a little bit more just lecturing. All of these numerical methods I'm talking about are going to be true in almost every kind of textbook you can find in an online course. So, goal here is for me to provide sort of the high level overview. And honestly, we're in first thing you got to do in numerical methods. We've talked a little bit about why this is important. Computers have holes in the numbers. We're going to have issues, and error can build up both as in terms of the clock cycles that you're doing and your round off and truncation. Okay, so first thing up is roots. And when you're trying to find a root, what does this mean? So if you have some function, I'll switch to green, and you have some function like this, and you're trying to solve, this is f, and you're trying to solve, hey, when is f equal to, say, 2? Well, let's say here is 2. So you're trying to find when is f equal to 2. Of course, you have two places. It's the same thing as saying a different function, g, of x, which is f minus 2. When is it equal to 0? And we do this because it is way easier to find, from an algorithm point of view, if I get this right, where is a zero crossing, because ultimately this function, as I'm sort of estimating where it is, I actually know. So let's say here, if I just happen to guess A and I guessed B, I don't know how far away from the hole is. We'll talk about the algorithms to get there. Not the hole, the root, the 0. I don't know how far away it is, but I know between A and B there is a root because A is negative, B is positive. And so that's the algorithm we're going to do. And like I said, what I'm going to do here, effectively teaching the numerical methods, I'm not going to show you the Python, I'm not going to show you the MATLAB. Basically, all these numerical methods can be shown through the pen, and then understanding the consequences of the fact that all of our real numbers are actually not real. We have a whole bunch of holes in our real number system when we store it on a computer, out of 32 bits or 64 bits. So the method here, the first one, is sort of bracketing. Now, you will have issues. So, for example, if I had put different A over here, then let me extend this curve, okay? Then I might actually be worried that, I might say, hey, between A and B that are both positive, I might say there is no root. So that's the first trap here. And so it is really on you, the engineer, that the computer is not going to know that, dumbly. Now, if you build in an algorithm and you first say, hey, computer, between A and B, sample it 1,000 times, because maybe 1,000 is not a big number and the computer does that in 20 seconds, it can then be like, hey, I detected 2 crossings of 0 in 1,000. But if you're just asking the computer to optimally, hey, I'm a dumb, blind engineer, tell me if there's zeros here, the computer isn't going to know, like, is it 1,000? You want me to do 1,000,000 searches? You want me to do 10 searches? Because maybe 10 isn't enough to find that there's 2 zero crossings. So it's a little bit where you, the engineer, have to step in. Our AI overlords are not going to take over just yet. Okay, so you have to handle this. In fact, I would recommend the first thing you do is just plot it. Almost everything. First thing you do is just plot it and let your human eyeball see this. Don't even ask the computer. You just slice this function up into 100 and plot it. Yes, the computer could blindly tell you in 100 slices there's 2 crossings, but you, the engineer, can also do this pretty quickly. So that's sort of the first step. And then really the algorithms kind of start from there. And so the first algorithm is called bisection. And I'll sort of keep drawing this again as we kind of do different methods. And so let's just focus on this, just this one part of it, okay? So bisection, and I'll use now left and right. Instead of A and B, I'll use left and right. What bisection is going to do is first say, okay, here is the left data point, there's the right data point. Let me split the difference, middle, and evaluate it. So bisection is very simple, which the first check is saying is the function at left times the function of right. Is that less than 0? Why? That's because it's crossing. That means there's a cross. So that's the first thing it's going to check. And then step 2, it'll then say, hey, is f at left times the right less than 0? Am I crossing between left and the middle? Or is it the function at right times the function at the middle less than 0? Which one is this? So then there's an if statement in there. And in this one I happen to draw, it's on the left. And so you would then say, hey, it's on the left. You select this one. And then what happens that this is sort of the first iteration, if you will. And then the second time through this loop, this is now R, and this is left, and then this is the next middle. Okay? And from that point of view, then here's the next middle, and it would select, the second time, it would select the right one, not the left one. So this is very simple. One, it's guaranteed, like this is gonna find you the zero, but as you might see, it's doing it by basically chopping your interval in halves. Now, maybe that's not fast enough, but the important part here is it's gonna work. Like this, if left and right, so if the first thing is true, that what you told it, your bracketing method, it will absolutely find the zero. Now, it's not gonna know if there are two zeros or sorry, if it's two zeros, you would be positive. There may be three zeros in here. It's gonna find a zero. Again, it's on you to know if is it 1 0 or is it 3 zeros. Is there a little wiggle in there that I didn't draw? Okay, that's bisection. False position, in fact, I'm going to wipe out the screen here. False position I'll do right here. It's the same sort of thing. Got this curve. All right. And false position, so here's left, here's right. And false position is just a fancy way of saying, well, don't split it in two. Actually draw a line between the two and use that to estimate it. So this is false position. Okay. And then this is now not middle, but estimate. Okay. So you're going to draw a straight line, you're going to get estimate, and then you're literally going to repeat the same algorithm and say, hey, is this estimate to the, is it negative or is it positive? And so what's going to happen here, the way I drew it, the estimate would actually be negative. And so the zero is not between left and the estimate. The zero is between the estimate and right. And so the second round, this then becomes left. This becomes right, or stays right. And now your estimate, I mean, like you said, even drawing this, I almost can't draw it where your eyeball can see it from the screen. So this one is going to have faster convergence. And likely still be able to find the zero. You'd have to really get crazy to find a thing that would send it loose. Okay. Then we'll kind of show a few more here. The next one is actually called Newton-Raphson, after those two scientists, and using the same curve. There you go. Now on this one, you actually don't start with the left and the right. You start with an estimate. And then the algorithm is going to come into that estimate, and it's going to sample some small interval to get an estimate for f prime, the slope. And then it's going to draw from that slope, it's going to draw and say, hey, here is the next estimate for the line. Okay. So this would be that estimate 2. Estimate 1, estimate 2 comes here, it will draw a slope. There's estimate 3, it will draw a slope. There's estimate 4. And so this is going to converge sometimes faster, sometimes slower, but we have to watch out for this. I'm going to draw a different function, right? Here's a function. In fact, this is the one in the book you used I thought was phenomenal. This is the function x to the 10th minus 1. All right? And so where does it cross? It crosses when x is equal to 1. Okay? Absolutely. And so, but until then, this is like really, really effectively minus 1 forever. And then it crosses 1 and then it shoots off to infinity. So what happens if you picked the Newton-Raphson method and your initial estimate was 0.5 as estimate 1? It's going to come down here and it's going to pick off the slope of this, and the slope is going to send it off to like, I don't know, 5 gazillion. And then 5 gazillion to the 10th power is some massive number. And its derivative, its derivative will come back, but you may never converge, or you may have just absolute horrible convergence. Right? Here's another really nasty one. Okay, what if that was your estimate? Now here's a thing where it's got multiple crossings, and so what would happen here if this is estimate 1? is it might actually send you over to here for estimate 2, and then it might hone in on this 0. Okay? It's going to completely miss those 2 zeros. And maybe as an engineer, you were actually looking for the 0 that happened to be either, this one or this one. Like, in fact, you might look at this and be like, -0, or my cross, I don't care about the function that crossed it at minus or whatever. I was looking for the positive one. So this is, again, where you, the engineer, the AI overlords are not going to take over just yet. You, the engineer, need to understand the method you're choosing, what you're trying to find. That's why, honestly, plotting it, if you can. There are some times where you can't plot it. It's so complicated, so crazy. But it doesn't, it's not, again, computers are not magical. When I would teach this at the university, the biggest thing I always would drive home to the students is the computer's only doing it what you told it to do. Now, if it's broken and your code isn't working, it's still your fault, okay? I've only heard one story in like 30 years where it was literally the computer's floating point processor was broke, and the student got it working by going to a different computer, okay? But it's not the computer, it's you. Now, if you don't know what you're telling it, it's your own problem. Now, that's what you have to worry about in sort of higher level languages like a Python, like a MATLAB, is you're just calling these higher level functions. You don't actually know what the computer is doing, which it may be taking that MATLAB code and translating it into lower level functions. And then even that, right? There used to be a computer science day where you couldn't graduate with computer science unless you had a machine language course. Machine language is like all about, shift registers and then the inner workings of a CPU and how you shift it around, and all. It's stuff that we don't, even in computer science nowadays, I don't really teach. They used to, be aghast at that any student coming out with any kind of computer background that didn't know a little bit of machine code. So here, even at this higher levels, you got to watch out. It's a computer is only doing what you told it to do. All right. So the last one we'll cover is the Brent algorithm. So this one's Brent, and effectively, it's just really slick. It's I'll do it in green. I think I was missing my stick in the green. So it's here's left, here's right, and then what Brent is going to do is it's actually going to fit a quadratic, okay, to function, and it's going to take the middle point. So I didn't do that very well. It's going to take the middle point and it's going to fit a quadratic, okay? Quadratic, and it's going to solve for where that quadratic is 0. Okay. Man, I really didn't draw that well. It's a quadratic through the left point, the right point, and the middle point. Now it's going to do these error checks on it, and it's going to estimate the error, and if it gets stuck, it'll actually just flip over to a bisection method. But for the most part, what it's going to try and do is fit a quadratic every step, and only flip over to bisection if it got broke. So it's a cool algorithm. You can look it up on Wikipedia. The book, at least the book I was going through with this applied numerical methods, it's about the level you did it. But Brent this is the one that you're going to see kind of stuck in MATLAB is basically given. I think in MATLAB, if you say fsolve or something, it's some function like that, like just solve it. It's gonna go to Brent, okay, on a bisection method. And then in Python, at least with the NumPy set, it's BrentQ is the function. So go Google it. Google it in the MATLAB version or the Python version, whatever you're using. But this is the method that tends to have really good convergence. And then pay attention to whether it's MATLAB or Python. They all actually they will show you the function calls that are there. Like, yes, you have to provide it a function. Yes, you have to provide it a bracket in this case. And in Rassmann, you say a function and the estimate, but you have to either give it its derivative. So there can be a user applied derivative, or it can estimate it for you. And then the quadratic one, all of these will have all of these other numbers associated with it, tolerance and estimations and all this stuff. So if your code starts breaking, pay attention to that. And when if you're ever using these codes, a lot of times I'm just using Python as a sandbox for me to understand different things. It's different than, say, a production code, where you're actually, you're writing a computational fluid dynamics code or something, and you have to solve for built in there. There's all of these stabilities that happen when it's a production level code, and you basically need it to always occur. So it's not always easy. I've done some pretty complicated codes, especially when I was doing some thermodynamic calculations, and I was trying to use BrentQ to find it. And there are times where it's like, even this wasn't stable enough, and I had to really go in and kind of tweak it. So this is root finding. This is almost the basics of all sorts of stuff. And I really do this a lot. There are times where if I had some crazy function, it could be an analytical function, I could write it out. I'm not even going to try to solve it analytically anymore. I literally just write it in Python and then say, tell me the zero. Or I'll plot it and then just tell me that zero. I'm not going to work too hard anymore because I'm pretty conversant with it. So this is Roots. We'll see you next time as we keep diving into the world of numerical methods.